Hello. The topic of our project for deep learning course is called New Approach to GAN Optimization. You can see the list of team members at the screen. So deep learning can be viewed as optimization of loss function with respect to parameters of the neural network. And the most popular methods for this optimization are probably stochastic gradient descent and ADAM. In the project, we consider alternative methods for optimization. These are gradient sliding, quick prop, and ellipsoid method. And in particular, we try to apply these methods to training generative adversarial networks. Actually, training GANs is a two-sided optimization problem. We have the loss of discriminator network, which consists of two terms, and also we have loss of generator network. And as you see, the expectation is taken over the samples from the distribution. The true distribution or the noise distribution. First of all, we decided to consider gradient sliding because it is aimed at solving the following optimization problem, where target consists of two terms and where we can access first order information about the terms independently. Here you can see the assumptions on the regularity of functions. The method has good complexity estimates because it one of the reasons is that it can skip computations of gradient of f from time to time. And that's the advantage that reduces complexity.
Okay. In the first experiment, we considered regression problem. Since the algorithm requires defined above constants, such Lipschitz constants for loss as function of its parameters, we analytically found them for linear regression problem. You can see formulas on the slide, and details of derivations can be found in our report. For MLP derivation can be done in this way. So we used scaled by some factor linear regression ones, and they worked well. You can see that gradient sliding shows performance comparable with SGD results. Next slide, please. Our next experiment was related to one-dimensional GAN problem for mix of two Gaussians. Discriminator loss has two terms, one for real predictions and another for fake predictions. Since gradient sliding algorithm is composite algorithm, we considered one term as f function and another term as h function. We observed that gradient sliding fails on this problem. We support that the reason could be mentioned above problem of estimating Lipschitz constants for loss as function of parameters for neural networks. We tried out different values bearing in mind the following considerations according to formulas in algorithms. The larger the ratio Lm is, the less iterations of PS procedure will be done on each iteration of main loop. Therefore, the algorithm won't concentrate solely on minimization of H and will upgrade of F more frequently. Moreover, large ratio L above M implies large beta, which means that the solution of subtask won't result in large step. Another possible reason for negative result is the fact that GAN training is min-max problem, in general not convex concave, which implies additional difficulties. But we have some progress in this task. If we set f equals h equals half of discriminator loss, then gradient slicing shows convergence and works well. In this setting, we don't use gradient slicing benefits in composite acceleration, but we see that the algorithm have a perspective for further research. So gradient slicing don't use benefit in skipping gradient calculations, but it shows that it works. Next slide.
Another algorithm we considered is ellipsoid method. The idea of the method is to generate a sequence of ellipsoids that will have decreasing volumes, and the optimal point should be always inside the ellipsoid that is considered. Ellipsoid is defined by its center C and the matrix H. And the algorithm step is made as as it's written in the formulas, and it has a linear rate of convergence in case of convex functions.
Hi. The next algorithm considered was quick prop algorithm, which is mathematical optimization technique invented by Scott Fahlman in 1988. It was inspired by Newton's method, but the main advantage of the algorithm is that it doesn't need to calculate the second order derivative explicitly for every weight, which is needed in Newton's method. Instead, it gives a heuristic approximation of the second order derivatives, which gives much more information about curvatures of loss functions. And thus, in theory, the convergence should be much faster. The algorithm follows as the following scheme, which you can see on the screen. It uses gradients from the previous step and calculates the difference in the weights as delta W, which you can see in the first line, and then the simple update rule follows. The algorithm is elegant and simple, and in theory, it should give good results. Let's see how it's working on the real data. Please, following slide, please. So we've considered a couple of experiments, one of which was simple multi-layer perceptron. Selecting appropriate learning rates and then conducting the experiment, we've achieved the following results. On the left-hand side, you can see vanilla implementation of the quick prop algorithm. You can see that there are high oscillations in the beginning, but at the end it converges, but the results are worse than ADAMs and STDs. On the right-hand side, you can see improved version of quick prop algorithm, where we tried to mitigate the problem of oscillations by giving the by trying to start the algorithm with a simple SGD and then giving the update rule to the quick prop algorithm. It still has oscillation, but it converges much faster. Please open the next slide. Also, we've tried an experiment on generative adversarial networks. Here we can see on the left side, on the very left side, the original distribution and the reconstruction of the distribution using the GANs. On the very right side, you can see the loss function of the quick prop method. You can see it explodes after a few iterations, namely 50 iterations in this case. We could not make it converge. It always diverged, and it blew up after a couple of dozen of iterations. And the possible reasons for that would be the oscillation that you've seen in the previous slide. The oscillations might cause the algorithm to diverge. Yes.
So the results are as follows.
We move to the final. Slide. The results are follows. We studied and implemented 3 optimization methods that are PyTorch compatible, as they are inherited from PyTorch Optim class. Methods are Lance gradient slicing, the ellipsoid method, and quick prop. Also, we derived Lipschitz constants for regression problem for gradient slicing method. Gradient slicing and quick prop works well for simple regression tasks. Ellipsoid method failed in the experiments, probably due to bugs. You can find details in our report. And GAN problem turned out to be too challenging for the algorithms. That's all. Thank you for your attention.